ANSYS software video today. My name is Dan Vasilini. I'm the Vice President of Sales here at Mallett Technology. You may ask who Mallett Technology is. Well, we are an ANSYS channel partner, and we've been specializing in the sale, training, deployment, and expert usage of ANSYS software for over 30 years. Mallett has 5 offices located along the eastern seaboard in the United States. Today's recorded demonstration is going to focus on ANSYS mechanical simulation software. ANSYS is recognized throughout the engineering community as a worldwide leader in simulation technology, and our presentation is going to demonstrate how problems that once took days and weeks to set up can now be solved and accomplished in a matter of minutes. I'm going to now turn things over to Matt Mahalik. Matt is our technical sales leader here at Mallett Technology. Matt, the presentation is yours.
Thanks, Dan, and welcome everybody. Thanks for joining us today. And as Dan mentioned, we're going to take a brief 10 minutes or so and give a brief overview of ANSYS Workbench environment. This is what I'm going to present is a typical design problem that we hope that many of you are facing out there, and show you how ANSYS can help you in those design problems by analyzing a complete system. So this is really the core of simulation-driven product development, which we are really strong here at ANSYS. I'm going to start out on ANSYS Workbench project page, which is really the first step in the basis of our engineering knowledge manager, where we have a nice interface where we can set up an engineering analysis workflow. And all of our data management is handled for us in the background. It really allows the engineer to focus on the task at hand, which is really to simulate his design as it works in the real world, and not have to worry about what's going on behind the scenes in terms of associativity back to geometry, the necessary file transfers that have to take place between perhaps a CAD source and an analysis source. So this is really our project schematic. And the project that we're going to look at today is really a two-part assembly that we have shown here on the screen. This could be a small electronic packaging component. It consists of a top cover and a bottom cover, and these two pieces come together with a simple snap fit in 4 locations. I have the top cover cut away here, so we have a small post that rides down over a small boss here and snaps into place, and that really fastens the cover together. So what I have is perhaps the approach that many of you are using out there to simulate these kinds of designs. We've taken that top cover and we've cut it into 4 parts because it's pretty much symmetric about the 2 vertical planes there. And we might start with a geometry model like this. From our assembly process, we know that this post right here has to move about 1 inch or a millimeter and a half backwards as it slides into that. So we've set up some simple boundary conditions to analyze that. We've set up an intelligent analysis with that applied displacement at the tip and holding this top button here fixed. That might be where the assembler actually pushes on this lid to insert it into the bottom cover. And many of you may be running these types of simulations, and you can get the deformed shape and the deflection out of this, can verify that that part is behaving as you think it will in the assembly, and even predicting the stress in that post here, and seeing some elevated stress state there, but really nothing that is of concern from a design standpoint. And many of you may be making this decision to stop right there, but there are some pieces of information that could be a benefit for the design of this 2-part assembly. You're really not looking at what's happening in the bottom cover, nor are you learning perhaps what the assembly force is that's required to push this lid down into the base, into the bottom cover there. So that might be a requirement for aesthetic reasons. Maybe the assembler does this repeatedly, time and time again, all day. So that piece of information might be important. Also, maybe there are some issues during the assembly process where these parts don't come together real well. So what we're going to do, why not analyze the full the full two-part assembly as it's actually being inserted together. So that's what we're going to do. We're going to move to our ANSYS Space Claim geometry tool, where we've already set up that first piece. We're going to also allow ourselves to grab that bottom cover. And with ANSYS Space Claim, we have the ability to, as you can see, link to just about any CAD source, the native geometry files from any CAD source, or in this case, we're going to go to a step file of that bottom cover. And Space Claim is really shifting the paradigm between a feature-based parametric solid modeler. What we as analysts really want to do is, we're not always concerned about the features and the history of that model tree. We want to basically get our design into simulation as quick as possible. And by moving away from a feature-based modeler, we can work in an interface where we have a few simple tools like pull and move and fill and split, something that's less feature-driven and more of an ability to just grab objects from the screen, work on them, quickly eliminate the parts of the model that we don't want, and get to our final design that we really need to analyze in a much quicker way. In that process, we as analysts also want to be able to do some geometry simplification. Maybe take out rounds in the model where I don't need them. And we want to do that just by, literally just selecting them and deleting them from the model, rather than having to try to find that feature in the model that is, really what we're looking for. Just the ability to click and delete, maybe grab some surfaces, move them up to another edge or surface, and just go through and simplify that geometry to the point where we want to have it ready for simulation. Okay. So in here, the only other thing we have to do is maybe move that top cover up a little bit. We might also come in and grab some edges here and maybe ease those edges a little bit so that we can have a little bit easier insertion. And really all I'm doing is grabbing those edges and moving them to the point where they're a fillet radius. Okay, so we've got our little edge eased. We're going to go back and move that top cover up just a hair and get that part ready for simulation. Okay, so with those quick few steps, we're about ready to go to simulation. And with the ANSYS Workbench project, if we switch back to that, there's an intelligent link back to that source geometry. Our project status tells us that that model has been refreshed in CAD, and we're ready to go to our assembly and do a quick update of that. While this happens, we're going to basically be able to reuse a lot of the information that's already set up in our model tree in ANSYS Mechanical, such that we don't have to redo a lot of things. I've got that part in there. It's come in with the correct default material. A couple of these symmetry boundary conditions we're going to reuse and just duplicate or copy them and move them to a new surface now. Reusing that data as we have it in the model. Our intelligent mesh algorithms in ANSYS Mechanical have been set up to not only choose the appropriate element based upon our physics, but allow us to, again, focus the resources. Some automatic mesh refinement has been done on those fillet regions where we've focused our attention here. This displacement, I'm no longer going to push on that edge, but I'm instead going to change that to be operating on the top face here where the assembler might push that in. And that fixed support up there, I'm going to actually move to the bottom face. Okay, so with those few quick changes, we've got a model that appears ready to set up. And not to mention the fact that as I added that second part in the assembly, our automatic contact detection in ANSYS has already flagged these surfaces as potentially being in contact with the surfaces on the bottom part. So since this is a sliding interface, we want to make sure that we extend these surfaces to allow full sliding contact between all stages of the assembly process. And we can just make a couple quick modifications here. And for that much, we're going to model frictionless contact. And we're really going to let the robust contact algorithms in ANSYS handle the majority of this problem. I'm using a lot of the defaults right out of the box here. Very sophisticated algorithms that have been designed to work on a wide range of problems, whether it be frictionless or frictional problems. The defaults have been set up to allow quick solutions with those default settings. Okay, so we have everything set up. I'm going to go ahead and kick this analysis off. In doing this, we can either be solving these models locally to our workstation, or we have remote solution capabilities in ANSYS that will automatically take this model and send it off to a high performance computing machine somewhere else on the network. As this solution is progressing, we have the ability to monitor solution convergence behavior and get information from the solution as it's going. This is going to take a few minutes, so I'm actually going to interrupt this solution because we're a little short on time today. But I'm going to bring you back now to an already solved version of this model, where now we can see if I run an animation of that assembly process, we can see our snap fit coming into play. Everything looks okay from that view. We now have also information on what's happening in the bottom cover. We can validate that stress region there. And as we mentioned earlier, we can now retrieve that maximum force required to insert that top cover into the bottom cover. And we find that very early on in the assembly process, right as that beam is coming over that post, the edge of that post there, is when the maximum insertion force, and it's about 6.2 newtons. So everything appears to be okay in this design until we do a little bit closer investigation, as we should, and we look into this region here. And we've actually discovered that during the assembly process, because maybe the thin wall of this bottom cover, as I push on it with that post, it deflects outward, and the top cover is sort of turning inward to the point where we're predicting now interference at that assembly point. And we may have caught a critical flaw in our design that maybe we wouldn't have caught if we had just stopped where we were just analyzing the deflection of that insertion post. So here, I hope this gives you a quick example of the ease of use of ANSYS, the benefits of doing simulation-driven product design on the full assembly of components rather than doing piecemeal solutions on one or two components. We hope to have additional webinars such as this to show you more information on ANSYS, but we want to thank you for joining us today and hope that you've picked up some good information and have piqued your interest in looking at ANSYS products.
Perfect. Thank you, Matt. So just to wrap up our webcast, as Matt was saying, we'd like you to keep checking our YouTube channel for additional webcasts that are very similar in nature to this. We tried to make this one as short as possible, and we will go in depth into a little more detail in some other webcasts that will be published. If you have any interest in contacting us, there's both my contact information, my phone number, as well as my email address, and Matt's email address in case you have questions about something he showed here today. Once again, thank you for attending, and we hope to hear from you soon. Goodbye.